Hey everyone, and welcome to today's Explainer. So glad you're joining us because today we're unpacking some of the absolute most fascinating and honestly terrifying invisible forces of nature. We're getting right into Chapter 6, Pressure, Winds, Storms, and Cyclones. Seriously, if you've ever watched trees practically bend in half during a storm, or found yourself wondering how on earth a massive cyclone just materializes out of the ocean, well, you are in the perfect place. We're going to take the totally invisible world of atmospheric physics and make it completely visible for you. So, here's our game plan for today's logical little journey. We're starting with the basics of pressure, moving into atmospheric pressure, and then winds and air pressure. From there, things get intense with thunderstorms and lightning, the anatomy of cyclones, and finally, wrap up with disaster safety and preparedness. Okay, let's dive right into this with Section 1, Basics of Pressure. To really get a grip on the massive storms we'll talk about later, we kinda have to start small, like everyday life small. Think about this. Why do narrow school bag straps hurt your shoulder so much? You know the feeling, right? You've got a bag packed with heavy books, and those thin little straps are just digging into you. It is the absolute worst. But if you swap that exact same heavy bag for one with nice, wide, padded straps, suddenly, it's totally fine. The weight hasn't changed a bit, so what gives? Take a look at these students lugging those huge backpacks to school. The whole secret to whether they're in pain or just fine comes down to the strap's surface area. See, when a strap is narrow, the area is tiny. That means all the weight of those heavy textbooks is violently concentrated onto a super small patch of your shoulder. That intense concentration of force, that is exactly what pressure is. High pressure, localized in one spot, means major pain. So, if we want to be scientific about it, pressure is defined as the force applied per unit area. The formula is literally just force divided by area, and it's measured in pascals or newtons per square meter. This simple little equation completely cracks the backpack mystery for us. A smaller area directly equals higher pressure. Oh, and it's also the exact same reason a sharp knife slices through an apple like butter. The knife's edge is insanely thin, which shrinks the area and maximizes the pressure of your push. But hey, it's not just solid objects that do this. Liquids exert pressure too. If you fill up a plastic bottle and poke holes near the bottom, water's going to shoot out in every direction. Now, the crazy thing is, the pressure isn't about how much total water there is. It's all about the height of the water column above it. Basically, the deeper you go, the heavier the water pressing down on you gets. This is precisely why those massive hydroelectric dams have to be built with super thick, incredibly broad bases. They literally need that extra bulk to survive the insane liquid pressure pushing against the bottom. Which brings us right to Section 2, atmospheric pressure. Because honestly, does the invisible air around us do the exact same thing? Now, what's really mind-blowing about this number, 225 kilograms, is what it represents. That's about 2,250 newtons of force. Right this very second, as you were sitting here watching this explainer, the Earth's atmosphere is pressing down on just a tiny 15 by 15 centimeter patch of your head with the weight of 225 kilos. Our atmosphere is just this massive envelope of gases, and gravity is relentlessly pulling it all down straight onto our shoulders. So, yeah, you're probably wondering, if I've got a 225 kilogram weight crushing down on me, why haven't I pancaked into the floor? Well, you can thank your biology for that. Inside your body, running through all your tissues and organs, you have fluids and gases of your own, and these internal fluids are constantly pushing outward. It creates this perfectly calibrated internal pressure that exactly matches the atmospheric pressure pushing inward. It's basically an epic, invisible tug-of-war, keeping you from being completely crushed. All right, moving right along to Section 3, winds and air pressure. Let's look at how differences in this pressure create the winds we feel every day. Okay, so air exerts pressure. But here is the golden rule you have to remember. Air always wants to move from an area of high pressure to an area of low pressure. And this comparison brilliantly illustrates that on a local level. If you've hung out at the beach, you've definitely felt this. During the day, the sand and the land heat up way faster than the ocean water. That hot air rises, right? And that creates a pocket of low pressure on the land. Immediately, the cooler, high-pressure air hovering over the ocean rushes in to fill the gap. Boom, you get a cool, refreshing sea breeze. But at night, the whole thing flips. The land cools off super fast, the ocean stays warm, and the wind literally reverses, blowing from the high-pressure land out to the low-pressure sea. But wait, what happens when these winds escalate from a nice beach breeze into an aggressive, high-speed storm? Imagine a violent gale slamming into a fully closed-up house.
what do you actually think the biggest danger to the roof is?
It's actually wild, but the main danger usually isn't the wind crushing the roof down from the outside, it's the air inside the house pushing the roof up and off. It's because of the Bernoulli effect. Basically, when wind rips super fast over a surface, like your roof, it creates a pocket of incredibly low pressure right above it. But the still air trapped inside your living room, that's still at normal higher pressure. And remember our golden rule, that high pressure inside desperately wants to get to the low pressure outside, so it violently pushes up against your ceiling. If that roof isn't bolted down tight, it just pops right off. Honestly, that's why cracking a window during a severe storm can sometimes equalize the pressure and literally save your entire roof.
Okay, Section 4, Thunderstorms and Lightning. Let's see what happens when rising air and moisture get together.
Let's move to how this builds into one of the wildest light shows on Earth. Thunderstorms usually kick off in hot, muggy places. It starts with warm, moist air shooting up from the hot ground. As it climbs, it cools off, and all that invisible water vapor condenses into those massive, towering cumulonimbus clouds. Inside those clouds, it is total chaos. You've got intense updrafts and downdrafts throwing water and ice around, making them smash into each other. All that violent friction actually separates electrical charges. Positives usually gather up top, negatives down at the bottom. And when that tension gets to be too much, snap. The charges connect and you get a colossal spark of lightning. That bolt heats the air around it so incredibly fast that the air explosively expands. And that massive shockwave, that's the sonic boom we call thunder. Now, since lightning is always hunting for the absolute fastest shortcut to the ground, tall buildings are obvious targets. But humans are pretty clever, right? We came up with the lightning conductor. It's literally just a pointed metal rod stuck on top of a building with a thick wire running all the way down and buried deep in the dirt. So if lightning does strike, the conductor grabs it and acts like a VIP express lane. It gives millions of volts of electricity a completely safe, low-resistance path to just bypass the building entirely and vanish harmlessly into the earth. We've reached Section 5, the anatomy of cyclones. Brace yourselves because these are the most massive, violent weather systems on the planet. So what exactly happens when one of those thunderstorms over a warm ocean just doesn't stop growing? Just take a look at the sheer, terrifying power of this storm brewing. As the hot sun beats down on the ocean, ridiculous amounts of moisture evaporate and rise up. When that vapor condenses into clouds, it actually releases heat. That extra heat makes the air rise even faster, which creates a gigantic, gaping zone of low pressure underneath. Now all the surrounding high-pressure air frantically rushes in to fill that huge void. And because the Earth itself is constantly rotating, it forces this whole massive, violent system to start spinning. Now, the crazy, ironic thing about a cyclone is its dead center, what we call the eye. While the outer walls of the storm are just an absolute nightmare of howling, destructive winds and torrential rain, the very center of this monster is just eerily peaceful. We're talking clear skies, totally calm with incredibly low pressure, but don't let it trick you. That calm eye is literally the engine that is powering all the devastating devastation spinning just outside of it. And when one of these giants finally makes landfall, the aftermath is completely catastrophic. These relentless winds basically act like a giant bulldozer on the ocean, pushing a literal wall of seawater called a storm surge straight into the coast. We're talking a wall of water 3 to 12 meters high. It floods everything, ruins farm soil with salt water, and totally wrecks the drinking water supply. Then you add in the torrential rains triggering landslides and winds that just snap massive trees like tiny little twigs. Just for some perspective, back in 2020, Cyclone Ampon slammed into the coast with wind speeds peaking at an unbelievable 270 kilometers per hour. Finally, we are on to Section 6, Disaster Safety and Preparations. Yes, that kind of raw power is deeply intimidating. But listen, we are definitely not helpless here. So the crucial point is knowing what to do. If you live in an area that gets cyclones, how to use science and prep to actually survive? First off, trust the tech. We have incredible weather satellites, and organizations like the IMD are literally tracking these storms from space to give us advance warnings. When they tell you something, you listen. Second, always have an emergency kit ready to go. Basic meds, clean water, canned food. And third, don't wait around. The second an official warning drops, you get your family and you relocate to a designated, elevated cyclone shelter. Surviving a disaster is 100% about acting on the data way before the first drop of rain even hits. We have literally gone from talking about the annoying pressure of a heavy backpack strap to analyzing the roaring 270 km/h winds of a cyclone. And the craziest part? It is all connected by the exact same beautiful, unyielding rules of physics. So I'm going to leave you with this thought.
With all these incredible satellites constantly tracking the skies above us, how will you use this science to prepare your own home for nature's invisible forces? Thank you guys so much for hanging out with me for this explainer. Keep asking questions, definitely stay curious, and above all else, stay safe out there.